So let's start our discussion from where we left in the previous video. We were talking about different analytical instruments and how we have. So far, if you looked at, we talked about how the data to be collected, what are the important aspect we need to consider in terms of the data collection, and what is the importance of having the good quality data. So now once we have the data, how we make sense out of those data. So in this particular video, in this particular module, I will try to give you some examples of how the data is used. Again, these are just illustrative purpose, just to kind of get you thinking about how the data can be used in different ways. So let's get started. So when you try to work with the concentration, as I said very early in, I think a couple of modules before, we should be able to convert the chemical concentration based on dry weight and the wet weight, because that's one thing we need to do, because the dry sample, we like many times when we take the dry weight, it is based on the moisture, like the moisture content has been figured in. Wet weight, we have not factored the moisture content there. So it's a wet and dry. So that's we'll try to do some math here. So say for example, if in this particular case, if you look at, we have a sludge, sludge has a arsenic concentration of 0.6 milligram per kilogram based on total weight. So its total weight means it's not the dry, it's the wet weight. And the moisture content of the sludge is 80%. So sludge is, as typically we know, has a lot of moisture. So many times actually for material like sludge, we don't report moisture content, we report solids content. So solids content is like 100 minus moisture content. So in this case, the solid contents will be 20%. If you think of the solid contents will be just 20%. So out of 100, say 100 unit of this sludge, 80 unit is just water and 20 unit is the solid present there. So the dry weight, in terms of the dry weight arsenic concentration, so if the wet weight is 0.6, so how much will be the dry weight? So if you, again, most of these solid waste problems are not difficult problems. They are pretty straightforward. It's a solid, that's one beauty thing about this solid waste course, is the things are, especially if you need to make sure you understand the units and you follow the units correctly. And as long as you do that and do a mass balance, most of the problems are kind of a mass balance problem. So if you do the mass balance, you will be okay. So if you go for, so we had 0.6 milligram of arsenic per kg of the wet sludge. So that's, we have a wet sludge here, that's a total, isn't it? So we have a wet sludge, but we have to calculate the dry weight arsenic concentration. So dry weight means in terms of the dry mass. So if you think about the mass, we have 0.6 milligram of arsenic, that is the mass of arsenic in 1 kg of the wet sludge. Now if you want to convert that into the dry part, we need to know in 1 kg of wet how much is the dry. So for 1 kg of wet, we have 0.2 kg of dry. That I said like 20% will be the solid constant. So in 1 kg of wet sludge, we have only 0.2 kg of dry sludge, because the dry content or the solid content is only 20%. So if you do this, so your wet sludge and wet sludge will cross away. So whatever you left it is 0.6 milligram of arsenic per 0.2 kg of dry sludge. Or if you do that, your 0.2 will cancel with 0.6 and you will get 3. So here you get 3 milligram of arsenic per kg of dry sludge. So pretty straightforward. But many times I see students even making mistake in that. So you need to, so they get confused between the moisture content and solid contents and all that, and they mess up. So but this is how you kind of do that, where if you have to convert from the wet and dry. But why it is needed? Because many times you may, as I said earlier, most of the standards are based on the dry standards. Your sludge quality standard, your compost standard, or soil standards, they're all based on dry, because the moisture content may change. So based on dry, the numbers you can compare. But many times when you analyze certain samples, you will analyze them as it is. You will not, it will be just the wet sample. It will not be the dry sample. So you should be able to convert between wet and dry. So this is an example of how to do that. So that's one. And then, so you should be able to find the average of the mixed waste stream. So you will not have, for example, if you are working on a compost plant, you are trying to design a compost plant, you are getting waste from different sources. Waste may be coming from source A, source B, source C, and for the individual source A, B and C, you know their moisture content, you know the arsenic concentration, you know the lead concentration, but for the mix you don't know it. So, but you know in what ratio they are mixed. Say for example, if you have 100 kg of the feed coming into a compost pile, say 40 kg coming from source A, 30 from source B, another 30 from source C. So based on their percentage, you know that, you know individual mass. So again, you will do a mass balance, because all the arsenic that is coming from different sources will be there. They are not going to go anywhere, and the total mass will be in the denominator, and the total analyte of interest will be in the numerator, and that's how we get the average concentration. So essentially it's like a weighted average, and we'll look at an example for that matter as well over here. So in terms of the concentration, so if we have two waste components, we have a sludge and the wood chips. These are the two components we have. We have two waste component, there is a sludge and there is a wood chips. For sludge has a 100 milligram per kilogram, that's the lead, and that's on the wet concentration. So it's a 100 milligram per kilogram, that's in terms of wet, and the solid content is 10%. In the earlier slide we had that moisture content of 80%. Here we have expressed as in solid content as 10%. Just to there are different ways you can see in different problems. Wood chips, again 300 milligram per kilogram of lead, moisture content is 20%. So wood chips is not that moist, but sludge is sludge. This particular sludge, the moisture content is 90%. So here the moisture content is 90%. So that's so this is we have this two waste stream. Now if you are mixing these two waste stream, so this is two waste, like a waste stream coming in, and for some reason we are mixing the components in a 50-50 mix by total weight. So we are taking, say if you are taking 100 kg, 50 kg of the sludge, 50 kg of the wood chips, we are mixing them together, and if we want, the question is asking us that what will be the lead concentration in the dry sludge. So what is the lead concentration in the dry sludge? So that's what we need to find out. So for that, what we will do, again it's a standard mass balance problem, like where, so we have two sources, wet sludge and wood, which we are calling it wet wood. We know that 100 milligram of lead per kg of wet sludge times 50 kg of wet sludge, if we take total as 100 kg. So, and 300 milligram of lead per kg of wet wood, 50 kg of wet wood. So what we have on numerator, if you look at this carefully, and it's pretty straightforward. So what is this? This is the mass of lead coming from the sludge. This is the mass of lead coming from the wood. If we add them together, that is the total mass of lead coming to the mixture. And one assumption is there, that mass of lead is there in the solid, it's not there in the liquid. So even if you take the moisture out, the mass of lead is still there. So this is the mass of, this is two sources of lead, so source 1 and source 2, we add them together, that's the total amount of lead present in the mixture. Now, but we need to find out their concentration per dry waste. So we need to find out, okay, what is the dry mass from this and what is the dry mass from this. So how we'll do that? We have 50 kg of wet sludge. We know that dry is 0.1 kg dry out of 1 kg, so it's only 10% solids. So this is the dry mass coming from dry for the sludge, dry mass of sludge. This is the dry mass from the wood. So we add them together, so that's the total dry mass. So what we are doing a mass balance. Total lead on top, so this is the total lead. If we add these two together, that's the total lead on top. Here if we add the things at the bottom, that's the total amount of dry mass. And we get the number of 444 milligram of lead per kg of dry waste. So you should go ahead and do that, and you should get the same number. And if you don't, let me know. But I don't think so there should be any problem here. So this is how we can do it. So this is just for two waste stream. We could have 3, we could have 4, we could have 5, but we can just extend this problem like that. So these are these kind of problems that it's not, as you can see, it's not very difficult problem. You just have to make sure you do stepwise and follow the basic principles here, and that should be okay. So this is on like how to calculate that. And then if you have to go back between total and leachable, many times we are worried about what is the leachable concentration. If you remember from the TCLP test we talked about, where we are took the 100 gram of sample, added 2 liters. Remember the TCLP test, where how much we had a 100 gram of sample, 2 liters of the leaching fluid, then you let it rotate, and then you get the concentration of whatever x milligrams per liter, and this x milligrams per liter is whatever is the solid present here, whatever is the solid, or you can say, even say if you think about lead or arsenic or whatever lead and arsenic present in this solid phase, how much will go into this liquid phase. So once the things will move from the solid phase to the liquid phase. So how much will it will move to the liquid phase? That is called the leachable concentration. How much is actually leached out? So when they are in the solid phase, they are in some sort of matrix. So how much of that lead or arsenic will leach from this solid and go into the liquid? So that's called the leachable fraction. So that if we know the leachable fraction, we can calculate total as if we know the leachable percent, like at what fraction, say 20%, 5%, 10%. Usually you don't see much leachability. Anything more than 20 you don't see over there. So that is over there. So you don't see this leachable concentration showing up over that part, but any like a you will have not more than 10% of the leachable concentration. So and if you know the total, you can assume certain leachable concentration. And the worst case scenario will be what? Worst case scenario will be all the solids present. Say if we have certain amount of lead present here, the entire lead goes into the liquid. So that will be the worst scenario, where the entire lead present in the solid phase will go into the liquid phase. Normally it will not happen, but worst case scenario it is there. If you put a very strong acid, and it also depends on what kind of leaching fluid you have. For TCLP test we use acetic acid and sodium hydroxide. That's not a very strong acid, but if you put aqua regia, yes, most of it will go into the liquid phase. So depends on what kind of extraction fluid you use there as well. So I think we have a problem on we will have some math relating to that as well. So if you have a soil contaminated with lead based paint debris. Now lead based paint is we have been in India, I think it's still some of the paint being sold is based on lead. The lead compounds are there, but most of the Western world has banned lead based paint in 1976, if I remember correctly. So around that time. So around 1976, most especially in US and Europe, Western European countries, probably they did it a little bit earlier. But this lead-based paint is banned because you remember that the small kids, they will have if you have a lead-based paint on the wall, the kids has a tendency to like even peel things from the wall and then put them in the mouth. So lead will go into their body, and then as we know, lead is not good, especially for it affects the brain development. That's the reason. I think I've already told you that we have unleaded petrol now. Unleaded petrol is, that means what? We had leaded petrol at some point of time. So that's why it is unleaded now. So we don't use lead anymore in our petrol in our petrol. So similarly, we have many countries don't use lead in their paints. In India also there is some companies actually they advertise saying that they don't have lead in their paints, but I don't think it's really banned, or it may be. If I may be wrong, I'm not 100% sure on that. But say if that, but that's not doesn't matter for this particular problem. Here we are talking about there is a soil contaminated with lead-based paint debris, which means the source of lead is the lead-based paint coming from there. And we want to find out that below what total concentration would you know that the soil is not a toxicity characteristic hazardous waste for lead. So it is trying to remind you about the TCLP test. So it's a kind of a recap of the TCLP. So toxicity characteristic leaching procedure, that's the TCLP test. Remember that we talked about that earlier. So if you don't remember, go back and look at that slides or video. So this TCLP test, we take 100 grams and use 2 liters of the leaching fluid, and then whatever the concentration comes out, we compare it with the regulatory standards for the TC standard, and for lead it is 5 milligrams per liter. We talked about that earlier. So for this is the 5 milligrams per liter. Now below what concentration would you know for sure? So as I was just telling you a few minutes back, so if you try to do this worst case leaching scenario where the entire lead present in the solid phase comes into the liquid phase, that will be the worst case leaching scenario. So if we have a concentration in which say whatever is total lead present in the solid comes to the liquid, if we have a concentration less than that, that particular waste will never be a hazardous waste. So let's do the math and I will try to explain it again, and I think and just try to follow it. So there is so you have, so toxicity characteristic concentration for lead is 5 milligrams per liter. We talked about that TCLP uses 100 grams of waste. It uses 100 grams of waste and 2 liters of the leaching fluid. So 20:1 is the liquid to solid ratio. That's the typically used for TCLP. That's what is TCLP test requires. So here, say if we had X milligram of, what the question was, how much milligram of lead could be there in that lead based spent contaminated debris, which the concentration, what is the maximum concentration that lead based spent debris soil sample can have, so that it will not fail TCLP test. So that's what essentially the question was, so that it will not be a toxicity characteristic hazardous waste for lead. So let's assume that number is X. So X is the amount, X milligram of lead is there per kilogram, X amount of lead per kilogram of the soil. So we have X milligram of lead per kilogram of soil. So that's, we have to find out this X. Now what is the second term here? We have used 0.1 kg of soil and 2 liters of leachate. Now where this is coming from? This is coming from the TCLP procedure. Remember the TCLP procedure, just in the previous slide also like you take 100 grams, so 100 grams becomes 0.1 kilogram. Since here we have kilogram, I have put kilogram over here. So it's 100 grams, essentially it's 100 gram, and then 2 liter of the leaching fluid. So what we are assuming here, that entire lead which is present on this, entire lead which is coming from the entire lead that is coming from there is getting into the leachate. Entire lead which is present in the soil is getting into the leachate. That's no more lead left in the soil, in the solid phase. Every lead that was present went into the liquid phase. That's the worst case leaching scenario. So if that happens, and if the concentration reaches of 5 milligrams per liter, then there will be possibility in some scenarios, in the worst case leaching scenario, there will be possibility of this particular lead based spent soil debris to be a hazardous waste. So what is that concentration? That concentration, if you do this math over here, and this 5 comes from the TC limit, this comes from the TCLP procedure. So we get X to be 100 milligram of lead per kilogram of soil. So this is the max, this is the like a amount of concentration. If the concentration is below this, if the concentration is less than 100, if your X is less than 100, that means that under no circumstances it will be a hazardous waste, because even if there is 100% leaching, the TC, it will not reach the TC limit, even with the 100% leaching. So but if its concentration is above 100, there is a scenario, there could be a scenario, theoretically it is possible for it to become a hazardous waste, because the concentration will may exceed this 5 milligrams per liter. I hope I have made this clear. Again, watch this part of the video again if you have to read, kind of go over that too, and you can always ask questions as well. So this is again important, these are very, very important concept. These are just a small problems, but a lot of application based. Many times there will be a, what is the significance of this problem? Many times there might be a industry coming to you saying that like I have this particular waste, I have done this total analysis done, and my I don't have any other elements there, or lead is only lead and arsenic are the issues, or only lead is present, or it could be any particular element. Lead was used as an example here. Say even only lead is present and the total concentration I got was it's less than you look at the total concentration and you find that they are all less than 100 milligram per kilogram. And if the person is asking you, should I worry about this being a hazardous waste, your answer will be no, because it's even in a worst case scenario, this is not going to fail TCLP, so it will not be a hazardous waste, at least for the lead. It could be hazardous waste for some other parameters, but not for the lead. And same thing you can do for other elements too. So that's are the things you need to look at. So it's a very application oriented example problem. So these are the things that you will do when you are working when you're working for a particular company, or when you're working for, say, Environmental Protection Agency, CPCB, SPCB, and all those kind of stuff. So you could do the same thing for SPLP. We haven't talked much about SPLP. SPLP is a synthetic precipitation leaching procedure, which we try to simulate artificial rainfall, and that is done when we are trying to use something outside in the landfill. It's a beneficial reuse. When we go to the C&D part, don't worry too much about this SPLP right now. When we go to the C&D, only thing you remember about SPLP is it's a synthetic precipitation leaching procedure. It is used to simulate artificial rainfall. So whenever we are trying to use a waste material outside the landfill for any sort of construction activity, this SPLP test is, we can predict using this SPLP test whether what will be the leaching and how this can be like how the leaching can happen. We can dig the data, try to compare whether there could be a potential groundwater contamination and all those kind of stuff. So that's why when we do this SPLP test, we compare that with the groundwater standard. But we'll come back and spend more time on this SPLP thing when we talk about construction and demolition waste, because the C&D landfill, they are mostly like when they're exposed to rainfall, or we are trying to use C&D waste in outside of the landfill. So we'll talk about more in that context. And here, remember in that just now the problem that we did, we assumed that there is 100% leaching. That assumption was there, that we assume it's 100% leaching happening. But you can also assume that only a fraction leached. Because 100% leaching usually doesn't happen. So you can assume that 50% leached out, 40% leached out, based on the experience that you have. So you have, once you are working in an industry, you have worked for several years, you know that under normal circumstances, it doesn't really leach out. You have never seen more than 50% leaching happening for that particular metrics, that particular waste type. To make it a more, I would say, more realistic judgment, you can say that, okay, I'll assume it a 50% leachability, because that's the maximum we have ever seen happening. So, and then based on that, you can do the calculation as well. And we can do the calculation in the opposite direction too. So it's once we know the leaching, we can know what could be the maximum concentration happening and all that. So it can be done both ways. So these are some examples which is kind of relevant for that. And then we'll try to look at some of the statistics calculation. So this is actually a very, very interesting part where you do the statistical calculation often needed when working with. So many times what we do, we go out, you are trying to characterize a waste, you go out and collect some samples. More the heterogeneity, more number of samples you should collect. So you bring the samples to the lab, you have analyzed the samples and you get the data. Now you have to go from this sample mean to the population mean. And that's where your confidence interval comes in picture as well. So we'll look at an example of that. And this data set that I'm going to present to you, the two data sets, they are a hypothetical data set, and it's not the real data set. It's just to illustrate some points, but you may encounter something similar in a real world scenario as well. So here we are trying to do concentration. Whether it's a hazardous waste or a land applied, we do some statistical analysis. So let's look at them really quick. So when we as I said, very rarely the waste will be homogeneous. They are not homogeneous. So they are not homogeneous. Very rarely you will see homogeneous sample. So what that means, you do multiple samples to determine the representative concentration, and more the heterogeneity, more samples needs to be collected to get the representative concentration. So we already talked about that just now. So once the sample is done, then you try to find out, you analyze the sample, then you do some sort of central tendency. Again, from your, if you have not taken a statistics, or if you have taken a statistics long time ago, go and revise it. So there is a term like a mean, median, mode, lower confidence, and then you look at the sample distribution, whether it's a normal distribution, log normal distribution, and what the data will be used for. Those kind of things comes in picture as well. So in terms of sample distribution, we know this is a typical log distribution, that the bell-shaped curve, and this is a log normal where you have a tail extending on one side. So that's log normal distribution. So this is the log normal part. This is the normal distribution, which you all know. So now if you look at this data, so there is a, let's say we have done a TCLP test. Since TCLP is a very common test to use, so we have done some TCLP test, and on a, say, we collected some data sample, did some TCLP test, and we found these numbers. So as you can see, there is a lot of variability in the number. I think the minimum concentration is 1 and the maximum is 9, and so between 1 and 9 is the value that we have, and total number of samples is 29. So now if we want to try to look at how these samples, when we try to do some analysis out of that, so if we make a histogram of that, we see a similar shape as a normal distribution. So if you kind of think about this as kind of something going like this and kind of coming down that, so that's like a normal distribution, isn't it? We just looked at it earlier. So it's a normal distribution kind of curve. So and then you can calculate arithmetic mean, your median, your mode. So those things here, though, you get those numbers in terms of the central tendency, and there is a way to find out whether it's a normal distribution or not. Like I would say, there is a kind of a thumb rule to find out, and we'll talk about that. And then you have a second set of data set where we had some samples. Some samples were done where we have number of samples is 31, and these are the data. These are the data we got, and in terms of the data that we got, the minimum value here is again 1, but the maximum value goes all the way up to 20. So it's a lot more variability than what we saw in the previous previous distribution. So if we do the same histogram for this sample, we see the histogram more like a log normal distribution that you saw, like you have something like this, and then you have a long tail. So that's the typical log normal distribution, and then you can do this arithmetic mean, median, and mode for that too. So in terms of the thumb rule, what we do, first we try to check for the normalcy. So quick test to use to assess whether the data is normally distributed or not. So for that we do whether the mean is greater than the standard deviation. If the mean is greater than the standard deviation and the variance, so that's the one way of doing it. If the mean is greater than the standard deviation or the variance, we do that. If mean is not greater than both, the data set is probably not normally distributed. If the mean is not greater than both, it's not greater than standard deviation and variance, that means the data is not normally distributed. So that's the like the part for that part. So let's look at the data set. So data set first, again you go back and do this math yourself. I'm just you can do this. This is a simple math. So you can do this. Arithmetic mean is 4.83, standard deviation is 2, variance is 4. Since the mean is greater than both 2 and 4, so it is likely that the data is normally distributed. So that's for the data set 1, and we saw that when we plotted that histogram as well. For the second one, arithmetic mean is 5.32. Sorry. So arithmetic mean is 5.32. Standard deviation is 4.10, variance is 16. So since the arithmetic mean, although it's greater than the standard deviation, but it is less than the variance, so that means it is likely that the data is not normally distributed. So once the data is not normally distributed, we have to kind of find out, okay, so what kind of distribution it may have. With the histogram that we did, it kind of felt like it is a log normal distribution when we plotted the histogram. So once you do the handle data which is not normal, because remember that t-test, g-test, chi-square, and all those confidence interval and everything that we do, it is based on assuming normal distribution. So that you need to make sure the data is normal distributed, like the equations that we are using. So how do you handle the data which is not normal? First thing is check whether the data is log normal. So that's the first step we do, whether the data is log normal distributed. Most of the environmental samples, they are oftenly log normally distributed. So you don't see them log normal distributed. So how you do that? You log transform the data. You take the log of the data and do this histogram again and look for mean, mode, median again, for check for normalcy, normality or normalcy again. You do that. And so if we do the transform data set for the number 2, we found the arithmetic mean to be 1.46, which is greater than both the standard deviation as well as the variance. So it's since 1.46 is greater than this as well as this, so that means we are okay. They are most likely it is we can treat this data as original data as log normal distributed, and the log transform data is normal distributed. So that's typically that you see in most of the environmental samples as well. So once we have done that, there is a term called geometric mean. You may have heard about this term. Whenever the data is log normal distributed, when we take that e to the power of that data, like earlier if you remember, we had the arithmetic mean of 1.46. So the arithmetic mean for this particular is 1.46, but when we so that's the arithmetic mean for the transform data. So when we try to go for the log norm, like the original data, we call it a geometric mean, and that's this geometric mean is your this geometric mean data is like is 4.28, which is e to the power of 1 point whatever was the previous number. Let's see, what was that number? It was it's 1.46. So if you do e to the power of 1.46, you will get 4.28. So that's and this, since it is a log normal, we call them geometric mean, so that we can differentiate between the data set which is normally distributed and the log normally distributed. So if the data is neither log normal or log normal, we can find another distribution. You can use more advanced statistical method, non-parametric method. Will not go there in this particular class, but there are ways to do it. There are ways to handle it. You can talk to your statistics professor. So how we incorporate uncertainty? Say, let's assume that this whole data, we said that this data was for TCLP result, and let's assume it was for lead, because we have been using with lead just for our argument's sake, and we know the TC limit for lead is 5 milligrams per liter. So if we can take this data, arithmetic mean for data set was 4.83, the geometric mean for data set is 4.28, so they are both below 5 milligrams per liter. That means it's not a hazardous waste. So it's not a hazardous waste. So based on the limited number of samples that we have, we can somewhat we can say that it is not a hazardous waste. But there are, although this is a limited number of sample and the data is very close to 5, so maybe somewhat we are not sure whether this the mean that we got is very same as that will be the true mean, again from the sample mean to the population mean. So that's what we are talking about here. So for that we try to incorporate what is the uncertainty. So let's try to do that. And when we do this uncertainty, we need to do this upper confidence limit. So UCL is the conservative estimate to take about the data set. So let's and there is always some degree of statistical significance. So if we are interested in to find out 95% UCL, and again there is a formula for that. I will not go into derivation of that formula. I will just use that formula. Derivation will be covered in your statistics class. Should be covered in the. So this is the typical formula that we use, where the upper confidence limit at 95% interval or 90% interval, whatever you want, and so this is what we are trying to find out. It's the mean plus the t value, where alpha is the the degree of significance, n minus 1 is the degree of freedom, then you have the standard deviation divided by the number of square root of the number of samples. So that's the formula that is used for that. So to find out the UCL. So if you want to find this UCL, so for this two data set that we had, for the data set 1 we will find the UCL at 95%. So we just plug in the number 4.83. this is the t value that we got from the t table. We plug in all these number 29 number of samples, and we get a value of 5.46. Note that this value is higher than 5 milligrams per liter. So that's the interesting part here. And same thing if you do for the second set, again again we have to do this UCL on the log transform data. So that's why you see these data over there, and then you do e to the power of that 1.65 to find out the actual, and then again you get 5.19. So both of these data set, although when we took the sample mean, they were when we took the sample mean, the values were less than 5 milligrams per liter. But when we took this UCl, the values are more than 5 milligrams per liter, and the 5 milligrams per liter was the TC limit. So now we are in dilemma, whether it's a hazardous waste or not a hazardous waste. So let's discuss that a little bit more. So that's how you handle that. So in that case, what you will do, because managing anything as any non-hazardous waste as a hazardous waste becomes too much of a costly. So as a regulator, say if you are a regulator and you are looking at this data, how will you respond? What will be your what decision you will take? One thing could be that means there is a lot of heterogeneity in the sample, so probably we need to go back and do more sampling. If you are a highly conservative regulator, you will say that, okay, this is a hazardous waste because I did the statistics on it and I found that your data is above 5, although it is not too much above 5, though that's actually more critical case, and so I will consider it a hazardous waste. If I am the industry person who has produced this waste, I will say, since the data is so close and it's just above 5, and if you do the sample mean it is below 5, I think that it should not be considered as a hazardous waste, or I should be given more time, or more I will go back and do more sampling. Maybe rather than giving 30 samples that we did, we'll do 50 samples or 60 samples or even 100 samples, and that may come out to be cheaper than managing it as a hazardous waste, and then try to convince the regulator that this is not a hazardous waste, or ultimately we may find that it is a hazardous waste. So this kind of things will come up when you are in a practically doing things in the field. So that's the reason I wanted to illustrate that example, and I hope you like that. This is really interesting part of how things may come up. So with saying that, like just a small thing before we close up. So we talked about this detection limit earlier. So if we have the data below the detection limit, remember we talked about that you do the detection limit, and so if many cases the sample results will be below the detection limit because the numbers will come and they are many times reported as BDLs, which is the below detection limit. So how you handle them in the statistics? So if you are doing this kind of statistics like UCL calculation, how you handle them? Because below detection limit also is some information. So if we cannot put it as 0 because that's not correct, we talked about that. We cannot, if we just ignore those data set, because when you do the statistics wants numbers. We cannot just write BDL, it's in a text, and that will not be taken in an Excel spreadsheet when you're trying to do the statistical calculation. So we need to put some numbers there. So what numbers we should put? So there are different arguments for different people. And so there are essentially 3 things people do. Sometimes they assume it to be 0. They put the 0 number there, which is not really true, and you see rarely being used for that. And you don't. Some will do it as a detection limit. That again kind of goes to a little bit higher side because it may not be same as the detection limit if the value is below that. And many places, most common thing is to use as half the detection limit. So if the detection limit is 0.65, you use as 0.32 or 0.33. So that's half, means some data may be higher, some data may be lower, so you are kind of in the middle. So that's like a more we can say more realistic kind of approach. So that's how it is handled. So but there are different, and otherwise there are more rigorous statistical approaches there to do that. So you can use those as approaches depending on how important that aspect is. So with that, we will kind of close this particular discussion, and in the next module we'll start talking about, remember I told you that in this particular week we'll also try to talk about waste management rules. So in the next video we'll start talking about the new rule that has come up and how it is different from the previous rule, and do some discussion associated with that. So I hope you're enjoying this course, and thank you.